Greetings, Mathies. We're looking at 8-7 normal distribution. To start out, we can think about rolling two die and seeing what the sum comes out. You could get a 2 by getting a 1 and a 1, or an 11 by getting a 5 and a 6. And if you kept track of those for 10 rolls, you might see a couple of 2s come out, a couple of 4s come out, and this is the frequency, like the percentage that happens. If you did that for 50 trials, you'd see a more complete spread of values, and 200 trials you'd get a bigger spread, and 1,000 and 5,000. And what you might notice is that you get some values that show up more often than others, particularly 7, because there's 3 ways to get a 7, a 3 and a 4, a 5 and a 2, a 6 and a 1, where there's only one way to get these two, a 1 and a 1, a 6 and a 6. So that's much more challenging to have that happen probabilistically. This curve is something like a normal distribution, and I wanted to show that to you in this way, but also in a different way. This is a PhET demonstration called Plinko, and if you let one ball go, it can either choose to go right or left, and should have a 50-50 probability of going one way or the other. So it would be really rare for it to go all the way to the edge, because all of these in order would have to say go right, go right, go right. And that doesn't happen very often. Much more probabilistic that it goes right, left, right, left, right, left. And so if you start this happening on a larger scale, you start counting where these occur. This n is how many of these balls have been dropped, and this is the occurrence. This is this moving mean. Okay, so there it goes. I'm going to let this run in the background as we go and sort of see like what sort of shape comes up. But as you can tell, you're getting much more in the center, because the spheres have a probability that they'll go right, left, right, left, right, left. So most of them just filter down the middle. A few of them go out to the edges. If you let this go for a while, I let this one go for 2,000 drops, you start to get this shape, which is a normal curve. Sometimes we call it a bell curve. There's an equation for it. It's called the normal probability density function, and it's you don't need to know this equation at all. You need to know how to use the concept of this, but maybe you should know how to read this. This says x. Maybe x is the length of giraffe necks or something. X is distributed normally with respect to the mean and the variance, which is standard deviation squared. Anyway, these other pieces are just modifiers, because you make this shape either taller if all of your data is very centered, or long and wide if your data is very spread out. So a normal distribution curve is called a bell curve sometimes, or a paranormal distribution curve. You'll find that the things in the center are the mean. That's the average. So this is height in inches. These are everybody's in here is the average height, and this is like the number or frequency or probability of finding somebody of average height. You'd expect most people in here, and in fact about 70% are right in the middle. And you have a few people that are taller, a lot taller, and a lot shorter, but most people are right around the average. Some examples of normally distributed occurrences might be the dice rolling, like we were talking, or maybe IQ scores. It's easy to have a little bit higher or a little bit lower than average score, but there are few people, and so like this height represents the number, the probability, or the frequency of that happening. So lower height, lower frequency. Little tiny height, little tiny frequency. Not that many people that have a score much higher or much lower. Most people are right in here. Same thing with, like, pop. Kernels of corn popping. There's a few that pop initially, and then brrr, most of them pop in here, and then there's always that last one at the end that pop. Anytime you have a measurement, you'll have some sort of bell curve about how the probabilities fluctuate around the mean. In normal curves, mean, median, and mode are all in the same spot. They're equal, they're right in the center, and the whole thing's symmetrical. If you really should have another axis, and this is the probability or the frequency of an occurrence. And so most people are going to be here at the mean. Maybe this is something like 40% of the people are right at the mean, making stuff up. And so then as you go farther away, there are 10% of the people that are at one standard deviation below. Standard deviation says how much difference between the values and the mean there are, like how much it varies. We'll talk about it a little bit later, but something with a curve with a high standard deviation would look like this, very spread out, and have a much lower mean. Right? Inflection points are very good. This has a lower mean because there are more people here and here and here and here, but on the purple curve there are fewer people and it drops off. But what you should know about all of them is that the area underneath is always got to be 1 because it's probability. So 100% of the time, 100% of the data should be in there. So that has to be the same as the area under there. So if you make the thing wider, you also have to make it shorter. Similarly, you can have low standard deviation, which means all the data points are clustered. And so a low standard deviation curve might look like this. Right? Like that. And this can't be 100, but this would be like 70%. Right? So 70% are here because as you go away from the mean, it drops off really quickly. And so here this would only be like 10%, right? And this joke, yo mama so mean, she got no standard deviation, means that if there were a mean, your mother would be so mean that 100% would be right there. She'd be 100% of the people would be right there, and no fluctuation outside. Math joke. So again, like I said, the area underneath is 1, and there's a great calculus application, but keep in mind these are probabilities, these are frequencies that we're talking about. So an interesting thing about them is the same values keep coming up regardless if your curve is wide or if it's tall and narrow, regardless of what's happening with the shape. Between the mean and 1 standard deviation above it, if you know those two, you can guarantee that 34% of your values lie within the mean and 1 standard deviation up, and also from the mean to 1 standard deviation below. It's just a given for all of these normal curves. Same thing if you go from 1 standard deviation to 2 standard deviations away. 14% of the data lies in there. Same thing below. This has an asymptote as x gets really big or really small. The asymptote is y equals 0 because y is a probability or a frequency, and you can't have an infinitely long lemur tail. It's a neat calculus application, which we'll get to later, in that if you integrate from negative infinity to positive infinity, which you can do, even though it's not a number, you should get 1 because 1 is the area under the curve. Some of you are starting that in your IAs and such. So let's try it out. I've got a catapult that's firing flaming pumpkins, and we're trying not to change the distance, but like the pumpkins are going to land at different distances. So the average flight distance is 80, the standard deviation is 15. What percentage of pumpkins travel these distances? Percentages, like what's the probability? Okay, I don't know how to do that yet, but I do know about how these curves work. So I know that our mean value is 80. So when I see a problem like this, I make a bell curve, even if it's terribly done by a mouse like that. Right? Make a bell curve, mark the middle, 80. So here's 80. And then the standard deviation is 15. So I'm going to move off a little bit, make another line that says standard deviation is 15. That means this distance is 15. That doesn't mean that spot is at 15. It means that spot is at 85, 95. Cool. So what percent of pumpkins traveled less than 65? If they're engineered nicely, this will be a integer multiple of 15 away from 80. So if you go 1 down, oh, this is 85. We added 15 to get here. If we subtract 15, this will be 65. And so what percentage of pumpkins traveled less than 65? Well, these and these and these. Add them up. So 14, 15, 16. That's where we get our 16%. Not bad. Okay, what percentage of pumpkins traveled more than 110? Well, we haven't hit 95, add 15 more to get to the next standard deviation. Oh, that's 110. And so we're looking at more than 110, so that's 2 and a little bit. All right, so great, there's 2 and a little bit. And then between 60 and 80, 60 and 80, between those two, 65 and 80 would be right here. So 34%. Boom. Cool. So at first, we can use the principles of the curve to see this happening. And we need to be able to visualize it like that to make the rest of it make sense. Here's another example. You have chest measurements, so like the distance around your torso. It has a mean and a standard deviation. So I'm going to use the standard deviation concept curve and work with that. So I know that the middle is 95%. 95 centimeters around, and that a standard deviation is 8 units. And so this isn't going to be 8, this is going to be 103, and another standard deviation away, another 8 is going to be 111. Oh, and a standard deviation down minus 8 is going to be 87, etc., etc., etc. And then we can use that to solve some of these problems. Like, what's the percentage of footballers between 87 and 103? Oh, between 87 and 103 is right in here. It's 68%. Right? This plus this. What about between 103 and 111? Here's 103 and 111, 14%. Same thing with B. Find the probability between 87 and 111. Add those probabilities up. Find the value of k such that 16% is below k. Okay, so they're asking for an actual like chest measurement, like 92 or 101. I'm looking for a boundary of 16%. Well, here's 14, 15, 16. So right up to here, this is 16%. And so 87 has to be my boundary. So k value is 87. But what happens if they asked about the same thing and but they said not between 103 and 105, but between 98 and 109, right? Here's 108 and 109. There's data taken for that. These are helpful. I kind of have them in my head because I use probability a lot, but I don't know like how far this. I can figure out how many standard deviations this is away from the mean, but these are not nice integer standard deviations away from the mean. So we need something else to work with that, and we're going to use tech to do that because your calculator knows those. So there's 3 tricks I want to show you. One is finding exact, precise. One is finding a range between 2, and one is finding the inverse, which is sort of backwards. And so here's the first one. This is a standard example. So the leg lengths of lemurs or something are found to have a mean and a standard deviation. Great. What's the probability of having a leg length of exactly 12? Well, I don't know if you made a costume for a lemur and it only fits a lemur with a leg length of 12. I don't know why you need this information. I'm just a statistician, so this is how you'd work it. With your fancy calculator, you'd go in and say second vars, and we're looking at a normal PDF, CDF, inverse normal. We're going to use normal PDF, probability density function. I think about the P as precisely, though. I'm looking for precisely an X value of 12. I know my mean was 18. They've given that to me. And I know my standard deviation, how spread out the data is 7. Go paste, paste. And if you have an older calculator, you have to memorize the order in which to put them. I got 4%. So you have a 4% chance of picking a lemur out of this group and having it have an exactly 12 centimeter long tail, right? Precisely 12 centimeters. Neat. Not that useful. Normal CDF is for cumulative, right? So it's like from one value to the other, and this is a standard example. Same mean and standard deviation, but now they're looking at leg lengths between 11 and 25. So you do the same thing. Oh, here we go. Where are we at? 10,000. Good. Good. Oh, and it's looking more like this normal shape. you would do in your calculator second dister, and we want CDF, we want cumulative. We could do this a bunch of times. We could do 11 and 11.1 and 11.2 and 11. And 24.9 and 25. We could do all of those, but why not? That's what your calculator is doing for you. So go down to CDF, hit enter. Lower limit, I'll tell you about this, negative 1e to the 99. Put 11, upper limit 25, mean and standard deviation that we know before, enter, paste, paste, boom. And so 68% chance of getting, let's see, this was 18, 11 would be down here, and 25 would be up here. So this probability that we just found, 11 and 25, is 68%. So we're putting in limits and getting out percentage. If for some reason they said, what's the probability that the lemur will have leg length longer than 25 centimeters. So I want this from here up. Then you do the same thing. Because it's CDF, you're still adding. You can go CDF, and the lower limit would be 25, and the upper limit would be a really big number. You don't even have to put anything specific in. Just put in a really big number. By the end, you're changing like the 10th decimal. So it's not a big deal. 18 and 7, don't worry about how many values specifically in there. And so like 15, 16% are above this. Likewise, you could do this by second dister. If you're looking for below 11, you'd say the lower limit, you could say negative 9999999, a really small number. It should be 0, but because leg lengths. And then the upper limit would be 11, and you could try it that way too, right? 15% should be symmetrical. Ooh, it doesn't have to be symmetrical. Happenstance. Okay, so put in limits, get out percentage. Put in location, get out percentage. Going backwards, like this question, you need to do the opposite or inverse, and that's the inverse normal. And so this is like the question that they would ask you: leg lengths, mean, standard deviation. The smallest 30% of lemurs have legs shorter than what? So I want some value k, and I want this area to be 30%. All of these values are well known, but there's no use in memorizing them. They used to be in books and stuff, and now instead of having them in books, we have them in our calculator in second dister, or vars. Go to inverse normal. It means I'm doing it backwards. I want the area to be 30%, has to go in as a decimal. Percentage, same mean and standard deviation. Left, right, center, I think leave it left. I think most of yours won't have this in here. And so this is 14.3. That means this location, the middle was 18. This location, this spot is at 14.3, where you get a boundary of 30. Now, most of your calculators are reading from negative infinity up to this boundary. So if this prompt was different and they asked you the largest 25% of lemurs have longer legs than what length? So we'd essentially be looking for this over here. I want this to be 25%. What is this spot? I know this is 18. Most of your calculators only go from the bottom up and fill until they hit whatever value you want. So if you put in 25 here, if you did the same thing and you put 0.25, it would find you a value down here. And it would tell you a tiny leg length, and it wouldn't make sense. So sometimes you have to front load this, these problems and say, okay, well if this is 25%, then I need the opposite half, which is 75%. And you plug that into your calculator, and you'd say, boom, I want this, but with 75. Yeah, 22. Okay, so this is 18. We should be above 18, so 22, so that makes sense. There's a couple other problems that I'll show you in another video that's attached, but I didn't want this one to go too long, although I feel like it has. So check those out. and we'll work through them with the calculator. Cool. On your home learning, you're going to do this normal distribution one. We're going to skip number 1, 2, 11, and 12 to do with z-scores. Cool? So yeah. Oh, he left it going. How do I order a pizza on this thing and charge it to Gorkevich's account?